We're going to go ahead and get started, so thank you everyone for coming. Get my clicker, and I'm going to try and stay in the insanely bright light, but I don't know how well I'm going to do. So thanks again for coming the post-lunch coma hour slot. My name is James Faulkner. I'm an application development technical evangelist at Red Hat. I run the App Runtimes products group within our business unit, and I do technical marketing, and I do stuff with containers and developers. I'm a Java developer. I did 15 years of Java development at Sun Microsystems, go Sun. I spent 6 months at Oracle, and then I had a brief stint at Liferay. You may have heard of Liferay, an open source portal, and I do some writing and speaking on the side, like I'm doing now. You can see my contact information at the bottom. If you have any questions, feel free to reach out. So digital transformation is real. So how many of you have heard of the term digital transformation? Yeah, pretty much most of you, right? Anywhere from banks to logistics to airlines. You've all heard this, and you probably collectively roll your eyes at that phrase. It's kind of meaningless from the perspective of DevOps and application development. But just to give you two examples, a little bit of humor to start us off here. So what do I mean by digital transformation, and what does most people think of? So this is an example of agriculture. This is a farming company who, through the magic and availability of drones and high-resolution imagery, they can take pictures of their crops, look at the colors, look at the infrared signatures from their crops, and then decide where to most effectively water those crops, saving money and improving their bottom line, right? So they're using technology to drive their business because it's available to them and it's easy and it's cheap and it makes a lot of sense. This is not digital transformation. So this is a bathroom checklist for a custodian who cleans bathrooms. And to digitally transform, they moved the checklist from the wall to an iPad on the wall, right? That's not digital transformation. You can't simply take the coolest technology available in the day and just use it as is and then declare victory over your digital transformation. So that's the end of the digital transformation pitch. It is real. We have a lot of customers, Red Hat, of the global 2,000 customers. Can anybody guess how many run Red Hat technologies? It's 2,000. So we have a lot of customers going through this pain and transition, the same ones that you guys are doing. So hopefully some of the lessons we've learned we can help to help you guys as well. So let's get down to the nuts and bolts. So this is a DevOps conference, it's Jenkins World. We do a lot of CI/CD pipelines and stuff like that. I'm not talking about that. That's all really good. We do a good job collectively as an industry. I'm talking about the applications that are on top and the applications that you run in your networks or on your clouds, and some of the things that you need to think of when you're doing digital transformation or breaking a monolith up and things like that. So to give you a bit of background, so traditional application servers, yes. Oh, sorry, see, it's freaking bright. So traditional application servers, for the last 15 years, you've had whatever app server you want to use, as long as it's one of those two in the upper right, as long as it's a Java EE or Spring. For enterprise Java, enterprise applications in general, also .NET is in there as well. But traditionally, it's a very limited set of choices because the way application servers came to light and the amount of money it costs to run them is pretty high. So IT departments and companies kind of force you to use the technology that they've paid for, and they can't really afford to kind of do whatever you want. That app server provided a lot of logic, a lot of functionality, distributed transactions, logging, resource abstraction. So they essentially provided both the application level business logic services as well as the application infrastructure services like clustering or high availability, things that application developers don't necessarily care about. So what's happened is over the last 4 or 5 years, a lot of new technology has come to light. It started with, you can take your pick of where you want to declare the epoch time, the zero epoch time of where technology started to take off, but generally for application development, we started to depart from the world of strict app servers and monolithic app servers somewhere in the neighborhood of in the early 2000s, mid to late 2000s. It really took off with the introduction of containers and microservices, especially with the Docker, the Docker revolution that began 13 years after the introduction of the concept of containers. Docker made it super easy to use, and so people started to building these lightweight microservices or lightweight applications using lots of different technologies like JavaScript, reactive programming APIs, and now we're starting to see the evolution march towards serverless, and I'll get into serverless later on in the talk. So essentially, the technology choices have grown, and developers have demanded more choice because of these technology choices that are better than what they were forced to use in the past. So similarly, from the application server itself, we are also seeing a transition. So we're moving from monolithic application servers that do everything under the sun and cost lots of money and lots of time and resources to run. We're seeing that split. And the split, the boundary is from the application infrastructure on the right in this diagram. This is where a lot of you probably live, in the CI/CD and DevOps world. And then the application runtimes, frameworks, and services on the left. So that natural split means that the app servers of yesterday are redundant with a lot of the capability of today's infrastructures, primarily based on containers, Linux containers, and virtual machines, and lots of technology that has come to replace the functionality formerly found in the app server. So you'll notice in this previous slide, we've gone from traditional application development to now we talk a lot about cloud-native application development. And you all probably heard this term before. There's various definitions. At Red Hat, we like to think of cloud-native applications as having these 4 characteristics. So the 2 on the left are primarily focused around characteristics that a developer cares about and knows about. And the characteristics on the right are ones that IT and application operators care about. So for the left, we have architectures. So for a cloud-native service or for a cloud-native application, it should be service-based. That doesn't mean microservices. It just means that the functionality is split into services and exported as services through well-defined APIs. This is no different than the software engineering that we've done for 20 or 30 years. The second one on the left is the communication style, so asynchronous communications. It allows more flexibility and resiliency and fault tolerance for these applications and performance. As I mentioned earlier, as we march towards serverless, the asynchronous nature of applications is that's kind of the end game, at least from the asynchronous perspective. On the right side, we have characteristics for apps that are important to operators. So the use of containers. We strongly feel at Red Hat that containers are the future. We have a lot of our customers not on containers. They're running bare metal, they're running virtual machines. Totally fine, but we believe for a true cloud-native application, it needs to be container-based because of the benefits and the characteristics of containers that make it possible to develop applications and deliver them out to the world, out to production in a sane and careful and versioned and controlled manner, which is much more difficult to do with VMs. It also introduces the isolation between different containers, and the density that you can get allows operators at least to deploy a lot of containers side by side and orchestrate them with platforms like Red Hat OpenShift or Pivotal Cloud Foundry or GKE or AWS and so on and so forth. And the last one you guys all know, the cloud-native applications are developed through a process, and we kind of collectively think of that as DevOps. There's lots of definitions of DevOps and what that means, but essentially it means the ability for applications to move through well-defined pipelines across the dev and ops boundary and be able to be managed in that way. Okay, so let's talk about application services for developers. So the traditional application service, in this case, we're talking about a cloud-native application. As I mentioned before, the functionality of app servers have been split, and so when you run an application today, it might not and probably isn't running on a traditional heavyweight Java EE app server like WebLogic or WebSphere. That doesn't mean that the functionality that those app servers used to provide are no longer needed. You can't just wish away the need for distributed transactions or application clustering or failover or session replication. Those things still need, those are important concepts for applications. And so around these new style microservice container-based applications are these services that you need, like discovery, like how do you find the other service that you need to talk to? How do you invoke it? How do you recover when things go wrong, when an application dies? How do you automatically scale up, right? So elasticity and resilience. How do you develop and deploy these out to production through a pipeline? Authentication, logging, it goes around the circle, all capped off with an API management system to kind of be able to control and limit and authenticate and analyze the use of these services through their APIs. So there's lots of services that you still need today that are not provided by things like Kubernetes. Sorry, by things like the runtimes in the middle, like JavaScript, right? Node.js. It doesn't have all this stuff. So that's sort of the 1.0 era of microservices. The things around the circle, we basically have had people like Netflix. The Netflix open source libraries have been very, very popular for building microservices, and they handle a lot of this stuff like service discovery and invocation. We have cloud platforms like Amazon Web Services that handle elasticity and resilience, but there's still some blanks, right? There's still some things left over that have not been filled out yet. So, but in the 1.0 era, we had awesome things like, as I mentioned, Netflix OSS. So if you need to do cloud, you have Spring Cloud Config Server. If you need service discovery, you can drop in Eureka and Ribbon and do client-side load balancing and service discovery. If you need fancy routing between these services, you can use Netflix Zool. If you need a circuit breaker for resilience, you can drop in Netflix Hystrix, a very popular circuit breaking library. If you need tracing and visibility, we have Zipkin, or now Open API or Open Tracing. All of this stuff kind of sits above the infrastructure. The problem with this approach in the 1.0 era, it wasn't really a problem initially because it was awesome and we never had it before, but as we move forward, the problem starts to reveal itself. And the problem is that all of these things are, in this case, Java only. If you're writing your application in Python or .NET, you're screwed, right? You don't get access to these. You cannot import Netflix Hystrix, at least at the beginning. Only if you were a Java application could you do this. So if you're writing in Python, you go and look for Python modules that implement some of these functionalities like circuit breaking or externalized configuration. In some cases, you find them. There's a random smattering for Python. There's some for Node.js. There's some for .NET. The other problem with this approach is that all these things are things that you as a developer have to deal with. So you have to drop in these libraries and you have to code your circuit breaker into your application, into the business logic of the application. That's a serious problem because as developers, we're not really good at that stuff. We're good at writing business logic, but we're terrible at figuring out, okay, how long do I need to wait? If I call a service and it fails, how long do I need to wait? Should I do an exponential backoff? What does that algorithm look like? How many times should I try before I give up? Should I just fail and return an error back to whoever's calling me and result in a big giant error message on a web page? So there's a lot of burden on developers using the 1.0 era. So enter Kubernetes. So Kubernetes was from Google. They experienced a lot of this pain themselves, and they decided to do something about it. So they started and then ultimately open sourced Kubernetes, a container orchestration platform. So now you can deploy your containers and manage them, and they can be elastic and resilient, and you have all these awesome features of the platform that allow you to do some of those services that you remember from the wheel here. So discovery, has an ingress and egress controllers that allow you to call microservices inside of the network as well as outside the network. There's elasticity, so it can automatically scale. It can deploy new applications to meet changing load and then undeploy them when that load goes away. Resilience, so when things die, Kubernetes has APIs for being able to detect that and then recover from that and spin up new copies of applications when the old ones die. But as a developer, you're still kind of left with some of the burden of dealing with retries when things fail. Kubernetes doesn't do anything in that space for you. So in the 2.0 era, I sort of split that. I sort of drew a line where a project called Istio was introduced, and this is actually only about 1.5 years ago. How many of you have heard of Istio? Yeah, okay, maybe about 30% of you. So Istio is a service mesh. What that literally means is when you deploy applications to Kubernetes, they are deployed into pods. And a pod is just an abstraction that is wrapped around your application. A pod is deployed out to a node, which actually executes your application along with other pods in the network. And those pods have access to other pods in the network depending on access control. Essentially, a pod is one or more containers, container images, Docker container images, or Cryo or runc, which is the engine. But they're essentially container images which get executed on nodes in your network. So when you make a remote call, like an HTTP request or a REST request to another pod, you're going across the network inside of that cluster. What Istio brings is it attaches what's called a sidecar, and it's another container that runs alongside, hence the name, and it transparently intercepts all of the traffic to and from your service. So if you have a microservice with, if you have an application with 3 microservices, each one of them will get a sidecar. And when your code makes an HTTP request, it goes through that proxy transparently, and that proxy can then do interesting things like stop the request if you're not allowed to call whatever you're trying to call. It can rate limit you. It can fail you on purpose for testing purposes, for example. It provides a lot of power to the operators of the service mesh to control your applications. Why is this super important? Because it's separate from your service. So for example, if you have 2 services and you want them to communicate securely, without something doing that security for you, you essentially as a developer have to write code which establishes a TLS connection, right? SSL, certificate management, all this stuff that you have to deal with as a developer to make that secure call. With Envoy and with Istio, now you can ignore that entirely and you simply make a call the way you would normally make a call in an insecure manner. So you just open a port and send a request. The Envoy sidecar will take your request, encrypt it, do all this key and certificate management between the services that are being called, do mutual authentication before it makes that call using encryption over the wire. And so you as a developer have no idea, nor do you care that this over-the-wire traffic is encrypted. You just know that it is. So it relieves the burden for developers for doing things like what I just described. It also allows you to do things like circuit breakers and bulkheads. These are common paradigms used for microservice architectures where you don't want to overload the system. If something is having trouble keeping up, you maybe want to stop sending traffic to it until it can recover and send it to another instance of the same service. Istio does all of this dynamically and transparently, and without your knowledge. You can obviously configure that. Each of the sidecars are connected to the Istio control plane, which allows you to configure them and say, how many times to retry, which services are allowed to call which other services. And so this proxy allows you to do lots and lots of awesome stuff. It's really, really magic. And it really introduced a new era of microservice computing, which is why I called it the 3.0 era. So we went from basic microservices to Netflix style to now we have Istio doing a lot of the heavy lifting of the really important topics for microservice developers on a hybrid cloud. So Istio brings in resilience, authentication, and tracing. The other stuff is still blank though. But what we're seeing is a natural progression. On the left is a traditional application from maybe 4 years ago. It's an application that has lots of logic inside of it alongside the business logic where it really doesn't belong. As we move to 2018, we're now seeing a lot of that logic being collapsed and removed from applications and application developers not having to care about it, and it's moving down into the underlying application platform, in this case, container platform, plus the Istio service mesh. So it really simplifies your developer burden, and it's something that you really should consider as you move into this new world of cloud-native computing. Okay, so the other bubbles which were blank, I've put some icons on here representing what a lot of our customers do. Now, not everyone uses all of these, but this is a very commonly used things like Jenkins, for example, for doing pipeline development of cloud-native applications. the EFK stack, the Elasticsearch or Elastic, FluentD, and Kibana for doing centralized logging and analysis of those logs. We have Prometheus and Grafana for doing monitoring. We have, obviously, Istio and Jaeger tracing for doing distributed tracing of your applications, both at the networking level, so which service is calling which other services, and even at the method level in the case of Java. You can do tracing across different methods and kind of see the control flow or the flow of your applications to do debugging or performance improvements, things like that. Then at the top, we have a number of vendors which offer solutions for API management. And we'll talk a bit more about API management and the importance of that later on as we start moving up the stack. So these are all technologies for the application infrastructure. Remember the image from earlier where I have the split of the traditional application server into infra plus services, and then business logic on top. So this is all the infra stuff. So then the natural question is, well, what about the rest of the story? What about the application services that you need? And that's where I want to spend the rest of the time in this talk talking about. So again, this image, super important to understand how we're moving from traditional to cloud native and that split between application infrastructure and the application services that it needs. What's not on this image is the actual application itself, which kind of sits up here above all of these services. So these are your business, this is where the business logic lives. This is where you want your developers spending most of their time and concentrating on bringing actual business value instead of just playing with the latest and greatest tools on the infrastructure side or the application services side. So what do I mean when I talk about application services? So here's a list of the typical things that application developers used to use in the world of monolithic Java EE or Spring or Tomcat or .NET app servers. Things like the runtimes themselves. So in the case of Java EE, it's obviously Java. Distributed messaging, distributed caching, authentication, identity and security. Business rules, so things like IBM Wodem or JBoss BPM suite, or a number of different BPM vendors have solutions in there. These are all the things that sit way above all the infrastructure. These are the things that you need to care about as you move away from traditional three-tier architectures where you have your presentation layer, your business logic, and then your database. So let's start with runtime. So there's a number of icons on this slide. These are the typical runtimes that you'll see out in the world. Node.js for JavaScript. Vertex is a reactive toolkit for Java. We have Java and Java EE itself in there as well. .NET, we have another reactive framework called Akka from Lightbend. On the upper right, the icon is a project called Wildfly Swarm, which is now an implementation of the MicroProfile specification. So MicroProfile is an effort by Red Hat and IBM and a number of other vendors in the Java EE space to sort of to give Java developers a path forward for microservice development. So if you're, how many of you are Java developers or use Java in your shops? Okay, quite a number. So MicroProfile allows you to move from the world of Java EE to the world of Java microservices and use all the same skills that you had in the past. So it has a number of APIs that are very familiar to Java developers, and so it makes it very easy to move from that world of old monolithic Java EE to the new world of cloud-native microservices. So a very cool thing. And then we also have Spring Boot. Spring Boot is another very popular runtime. Spring was a historic alternative to Java EE. And arose, and it's really taken off because of the slowness of Java EE as developers look to the future and they look at the slowness of Java EE and they see Spring as an alternative. So it's a really powerful ecosystem. It has lots of modules in there that implement a lot of the things that Java and Java EE developers need. And then the last one over there is DropWizard. So DropWizard was actually, if you've ever used fat jars or heard of fat jars or Uber jars, some people call them, DropWizard was actually the first vendor to make those available. So it's a very popular way of building and running Java microservices. Okay, so the point of this slide is not to show you that there's cool options. The point is to say it doesn't matter what you pick. It's up to you to pick the best tool for the task at hand, for whatever you're doing. Each of these runtimes has different strengths, pros and cons, and we could spend an hour or more going through all of them. But the point here is that you, as developers, you want choice. Companies and organizations want choice as well, but they want limited choice because you can't have every developer in your company choosing whatever they want, right? At the end of the day, you have to support this stuff. So it's important to make good choices, but sane choices depending on a number of characteristics. And here are the characteristics. So when considering what runtimes to use for the hybrid cloud development, number one, think about the desired workload and architectures that you want. If you have a highly distributed and transactional app, you might look at Java EE or Wildfly Swarm. If you are building a reactive application with lots of asynchronous messaging, you will want to look at reactive programming like Vertex or Akka or Node.js. If you have a ton of Java EE developers at your company today and you can't just fire all of them and hire different, you're going to want to pick a runtime that's compatible with the skill sets that you have in-house. You also want to consider the availability of copy-paste. If you're a developer, I'm almost positive that you have at some point gone to Stack Overflow and copy and pasted some bit of code into your code because it works and it got lots of thumbs up. So when you're considering runtimes to use, consider the strength of the community and the availability of smarts out there that can help you in your quest to build the next app. And then the last one is sort of the sad face one, right? It's the one where you have to use something because some high-level executive decided that the world is going to be JavaScript, so you're going to be stuck on JavaScript no matter what. So also another consideration when choosing what you want to do with your runtimes. Okay, so that's it for runtimes. Again, choose the best one for the best job. So the next thing is messaging. So in the world of microservices, in the world of cloud-native applications where we're splitting up our traditional monoliths into a set of containerized microservices that need to talk to one another, suddenly the network becomes important, right? Before you could just make an API call directly in the same virtual machine, whether it's Java or bare metal, and it would go lightning fast, and it's guaranteed to work, and it's compiled into, and linked at compile time to guarantee to be successful. In the world of microservices, that's no longer true. You now have this this network between these two services that may or may not be working at the moment that you make that call. So distributed machines, multiple applications running in different processes, and they need to talk to each other. So typically what we'll do is build REST services, right? RESTful services passing JSON objects over HTTP, which is, that works. For a number of applications and workloads, that can work, and that's where you kind of end your journey when you're looking at how these things communicate. REST it's well understood. It's typically synchronous. You expect an immediate response, and you pass JSON objects, and it's pretty easy to debug too. You just print it out on the console, or you use Wireshark to look at the contents of packets as they travel across the network. So that's cool. The problem here is the limitations as you move from a simple application to a bit more complex application, or you have, for example, if you're in a regulated industry, in a bank or a government, where that transaction has to go through or fail, and you have to log it and be able to audit it in the future. So you have limited support for sort of guaranteed delivery of messaging. So when you move to an application that needs this, HTTP and REST, they're going to fail you. So you've probably heard the phrase smart endpoints and dumb pipes, and that's sort of a mantra that's been repeated a couple of times in the cloud-native world. What we really need is smart endpoints and not so dumb pipes to guarantee, to give us some more flexibility and power in the messages that are now flowing across our network. In addition to messaging in general, as I talked earlier, the characteristics of cloud-native applications include asynchronous messaging. So asynchronous messaging allows us to really decouple our applications from one another and respond at the time we need to respond, as opposed to making a call and waiting for that to return. This is asynchronous non-blocking event-driven programming. It also provides capability to do things like multicast, to multiple services. You can do pub-sub with pub-sub messaging with things like Redis or JBoss AMQ is another implementation of that. So, and there's also a standard behind that. Just like there's a standard with HTTP, there's a standard behind asynchronous messaging. There's a number of different standards. AMQP is a protocol, is probably the most popular, implemented by a number of messaging systems like RabbitMQ in the Spring world. And it's an ISO standard, so it's one of those standards that's really well known and trusted by big companies that pay a lot of money. There's also ones like MQTT, which is really popular in the IoT world, and STOMP, which is simple text-oriented messaging, which is kind of a simplified version of AMQP, if you will, a very simplified version. So there's lots of options here to consider, but really the message here is consider whether HTTP and REST are good enough for you in terms of the requirements of your applications. Okay, let's move on to data and caching. So to give you a quick visualization, think about how long a typical pizza takes to deliver to your house or wherever you live. Typically, it's around 30 minutes. Now, we'll set that as the baseline. If that's coming over memory, it takes 30 minutes. If that's coming over an SSD, which we typically have in a lot of our laptops today, it will take about 3 weeks to deliver that pizza. If it's coming over a traditional hard drive with platters and moving heads, it's going to take about 5.5 years to get that pizza. So you can see memory is the new disk. Memory is still way faster than SSDs, extremely faster than hard disk drives, and it makes a lot of sense to store your data in memory whenever you can. So essentially, using things like a distributed data grid can put your application data in memory and make it very, very fast to access. It's read and write. So essentially, it speaks to the performance and availability of your data. If you have a distributed data grid, not only can you retrieve your data fast, you can make sure that your data lives near your application or actually in the same running instance as your application, running VM as your application, with technologies like near caching, which is a feature of many of the distributed data grids on the market today. So near caching is essentially kind of like Istio for your data, where there's a proxy. In this case, it's a cache that sits very, very close to your business logic, providing access to that data in the same VM. Obviously, there's a synchronization that needs to happen between the near cache and the actual cache, and then ultimately the backing store of this data. But caching is a proven technology for speeding up applications, and so the closer you can get your data to your business logic, the better you are off. An even more interesting application of data grids in particular are that they provide autonomy and migration tooling. And when I say that, it's super important because a lot of us are in the process of modernizing our applications. We're taking our monoliths, we're splitting them apart into multiple microservices. That process is, in some cases, very easy for the smallest of applications, but in the vast majority of these applications are managing and sitting on top of data stores that are monolithic. There's a single database. You're using lots of features in the database to make sure of the referential integrity of this data. And it's difficult to split it apart, as it's much more difficult to split up data than it is split up applications. So here's a very brief example of the difficulties here, and one of the things that you can do with data grids and data virtualization to make this easier. So here's a sample application, a monolithic application. It has 3 services, foo, bar, and cheese. All 3 of these services sit on top of the same database, and the objects or the records in this database for foo, bar, and cheese are normalized, so they don't have a lot of repetitive. In fact, they have no repetitive data. They have foreign key constraints. They have all kinds of indexes and very cool things in the database that allow these objects to be read and written into and from the database. Typical 3-tier architecture here. So let's split it up. So the first thing we're going to do is we're going to take the foo service and break it out of the monolith and create a foo service with a foo API on top. We're also going to modify bar and cheese. Instead of bar and cheese accessing the foo database objects, it's now going to call the foo API to do what it used to do with the data in the database. Then foo itself is going to read and write its own foo data from its foo database. Right? Can anyone tell me what the problem is with this approach? Sorry? Performance, yeah. So there's definitely going to be some latency from cheese going to foo database as opposed to cheese directly to the database. So performance is actually one of the more important ones. Sorry? I can't hear you. Single point of failure. So in terms of the foo service going down and not being available, yep, that's another one, good one. So there's actually a number of problems with this approach. Those two, performance and single point of failure, are super important. Another really important aspect of this is how much money do you think it's going to cost this company to take this database down and transfer all of the foo records from here to over here, and then repair the bar and the wine and the cheese records to like remove the referential integrity constraints from there, make sure everything works, and then bring it all back online. It's, you know, for larger companies, that's simply impossible. So there's lots of things that are wrong with this. As we talked about, the tables they're highly normalized, and they can have all these referential integrity constraints that really can't be broken very easily. Just because you've extracted the code doesn't mean that everything can stop so that you can go reformat all of the services that used to use those services. Essentially, the point of this is that it's an ugly migration, and it can't just be wished away. If you can shut down your entire system and refactor it all and then bring it back online, that's awesome. Congratulations. You don't need a highly paid consultant to come in and tell you how to do it. You just do it. But most companies, that's really not an option. So data grids and data virtualization technologies can help you in this regard. This is a highly simplified solution to this. There's a blog post link at the bottom from a person called Christian Posta. He works at Red Hat as well. He's a solution architect. And he's had a number of customers go through this process, and he's kind of distilled all of the smarts from those customers about what they did. Essentially, you can do what I described. It's just there's a lot of other steps in the middle, temporary steps, to avoid taking the database down, which involve essentially writing small backends that you write two versions of the backend, one with the original code and then one that knows about the new database. And you can link the new database. In this case, from the example before, the foo database is the orders database in this diagram. But essentially, you can kind of create this virtual link between databases as you slowly migrate the code. And then ultimately, there will be a point where you have to shut everything down and stop transactions from coming in so that you can move the code from the big database to the little database. But the steps in between allow you to learn about the granularity of these services that you need to write. And so it gives you time to iterate, as I said, as a development team before you make that final switch over. So again, a highly simplified version, but one that data grids and data virtualization technologies can help you with. So something to consider. Okay, so next one is integration. So integration, didn't we solve this already, right? Didn't we have ESBs, the Enterprise Service Bus? It turns out the ESB really didn't solve it for a number of use cases. There are process bottlenecks that occurred with an ESB. ESB kind of became the new monolith. When you needed to make a change to an ESB, you needed to contact the ESB team and wait a certain amount of time. So if you wanted to create a new microservice or change a microservice API, you had to involve this third-party team. So that kind of defeats the purpose of doing things like autonomous microservices. So the solution, one solution is an API gateway. This is a very common thing to do with microservices. When you have a number of microservices and you need to kind of make an aggregated result from a number of different microservices, you just put an API gateway in place. So all these microservices then go through the gateway. This should look similar. This should look very familiar to you from the previous slide. It looks kind of like a lot of the characteristics of what the downfall of ESBs are starting to creep up in the API gateway pattern. So there's actually a link there's a great article on this from ThoughtWorks, and they kind of talk about the the different characteristics of ESBs, what failed them, and why API gateways are not necessarily the best approach. So to give you some visualization, so this is the Netflix, this is from a presentation actually almost 2 years ago from Netflix, showing you what their microservice architecture looks like. They kind of ran some visualizations on the different capabilities. What they discovered was they were starting to go to the ESB. They started, this little guy here was sort of mediating a lot of the traffic from the outside world into their microservices, and every time they wanted to add a new microservice, they had to kind of contact this API gateway team and work with them to develop this new set of services. So they said, we don't want to go there. We're going to be back to where we were 20 years ago. So what they ended up doing was essentially splitting up the API gateway into different autonomous miniature API gateways owned by the teams that needed this functionality. So they started to follow more closely the value of autonomous services being developed by independent teams and being able to deploy them independently. And they were able to kind of escape from the pit of doom that you typically see with a centralized service. So this is a general observation on the benefits of autonomous development and deployment of applications. So at Red Hat, we've come up with a kind of reference architecture for modern integration. It does have a number of gateways. I know this is an eye chart. You're not expected to understand all of this. I have a simplification for you, but it's essentially a layered approach, right? It goes against what you think, because as we've moved from monolithic end-tier architectures to a set of microservices, we've gone from this layered thing to this web of APIs. But in reality, layers make a lot of sense, and I'll tell you why. It's a separation of concern issue. So you can have multiple teams writing autonomous APIs and services, but when they're deployed in a layered approach, and it allows you to manage these layers independently. So for example, the top layer here is the API layer. This is where you find your API gateways, the ability to do policy enforcement and rate limiting and quality of service guarantees, and more importantly, analytics of your APIs. But this is all independent of the nature and the business logic in the services themselves. So this top layer can be managed completely independent from all of your application infrastructure and application development teams. Then the second layer and the third layer are where your business logic goes. And this is where your business team, your developer teams that are writing business logic will deploy their applications. So you can have the foo, the bar, and the BAS service deploying components to these different layers. They're still building autonomous, independent microservices. They don't need to call the API team when they want to deploy a new service. They're able to do that independently and live in these two layers. So it allows us to separate these layers and manage them independently, giving us the ability to write these independent microservices and deploy them. Okay, last topic is serverless. I'll cover this briefly. So here's an image of a serverless server farm. Awesome. In reality, of course, you know that there are servers somewhere out there, either in the Amazon data center or Google or IBM or wherever you happen to be running. But serverless, how many of you heard of serverless and kind of have a general idea of what it is? All right, a lot of you. Awesome. So I'll skip the serverless definition. You can read it. I'll give you 5 seconds to read it. Event-triggered computing, where you don't have to pay for the hardware, right? You just pay for the execution time. Awesome. So why do we need serverless? It's really the end game. This is where we're all heading. This is where we at Red Hat believe microservices are, in some sense, a stepping stone. We'll still have monoliths, we'll still have microservices, but serverless is where the progression of application development is pointing at, because of the nature of cloud and costs and server farms and managing all that stuff. It really removes a lot of that burden from companies to have to deal with that stuff. It doesn't mean that you can take your microservice applications today and just turn one microservice into a serverless function, but it is definitely the end state in terms of efficient computing. So there's typical use cases like server management. When something happens, an app fails on an event on a server, it can trigger an event on your serverless platform, which can notify you via PagerDuty, file a Jira ticket, and then fire off an application written in Ansible to repair it or do something else. Also, So for example, you store an image at the bottom here, an image of an umbrella. Through machine learning, you store it, that causes a trigger. You can transform that image, do some analytics on it through a serverless trigger, and then kind of realize that, hey, it's an umbrella. Awesome. So all these things kind of should look familiar to you, right? It looks like a Unix pipe. Looks like a set of Unix commands that pipe the input of one from the output of one to the input of another. Essentially, these 4 lines are different serverless functions, and they do one thing, and they do one thing well, and when you stream them together, you can develop very complex and powerful applications using these simple primitives. So that's kind of what serverless can do for developers. It gives you these primitives that allow you to make calls and trigger events and do all kinds of asynchronous programming. We're essentially headed back to our roots, which is awesome. Great use cases, so processing hooks, data transformation like images and video and audio codecing, or encoding and decoding, chatbots, PDF generation, you name it. When you don't use serverless, right, the things that take a long time to run, serverless is, and things that can't deal with cold start time differences, like real-time applications, things that sit for weeks, like business processes that take 3 or 4 weeks to complete and require human input. Those are things not really suitable to the serverless world. So serverless is great, but it's not always the way you're going to develop applications in the future. Okay, so last slide here. So essentially my recommendations to you guys, choose the right tool for the right job, right? Consider the runtimes and the services that those runtimes need and the characteristics of those applications, what they require. Minimize the developer burden. So don't make your developers do things that they're not good at because you're going to get crappy results. Containers are really great. Containers provide a common language for dev and ops. Please use them. They're very powerful. You get a lot of functionality for free, especially with container orchestration like Kubernetes. Design for requirements. Don't kind of include everything under the sun just because you might use it one day. And then lastly, when you're breaking up the monolith, consider the characteristics of the microservices that you need and the things that you used to take for granted. The ability to make function calls inside a VM is now gone. So consider what to do when you need to make that, essentially the equivalent of that function call across the network. So think about what your applications need beyond just the services that you enjoyed in the past. So that's it. So thank you very much. If you have any questions, I'll be around for another 15 or 20 minutes. And we have a booth if you want to talk about and see demos of some of the offerings that Red Hat has. I explicitly didn't want this to be a sales pitch, but we do have some offerings that can help you in this world. So thanks again for coming, and we'll see you the rest of the show.